All right, so what we're going to look at here is we're going to look at inertial reference frames. And this topic has come up a couple times before, not in this class, but in Physics 110 we introduced Galilean relativity right near the beginning of the class. And then we brought it up again when we did some things with momentum, because elastic collisions are easier to solve if you consider reference frames. Of course, this stuff is vital for Physics 211 because you take relativity there. And this is sort of the segue to relativity, actually. A natural course of subject matter in this class is to take E and M and then immediately transfer into relativity because they have a lot in common. So, well, enough ideas in common that it's an important segue. So in this example here, we have two observers. We have Alec, who is considered to be the sort of stationary frame observer. We have Brittany, who is the moving frame observer. And Brittany's going to be moving to the right here in a magnetic field that's external. Okay, and so what Alec is going to predict is going to happen here is that when you do your V cross B, that the charge should go up, because V cross B is in the direction of upward, right? And so we should see this force push this particle up. Okay. Now, in Brittany's reference frame, however, the charge doesn't move because she moves with it. She'll still see an electric field, a magnetic field, but she definitely won't report. Well, it doesn't seem like we should say that we don't. It doesn't seem like we should report that there is a force upward on that charge there. But here's the thing: these are inertial reference frames. What that means is, one reference frame moves at a constant speed relative to the other one. And one of the aspects of Galilean relativity and, by the way, of special relativity is that forces all got to be the same in inertial reference frames. When you have accelerated reference frames, then there's some shenanigans that happen there. There's a little bit of tomfoolery, a little malarkey that you gotta sift through to reconcile some of the differences there. But this is definitely seemingly some kind of paradox here, whether we're going to see a force or not. We have to. If Alex sees a force, there's a force. Brittany's got to come up with something to explain this force. She got some explaining to do here. So we'll see how. Now, here's our two reference frames. They're going to have reference frame A, and reference frame B will be considered the moving frame here. It's going to move with the velocity. Now, I don't know if you remember these subscripts back in 110, but this is the velocity of B relative to A. That's what the subscripts mean here. And so we have an object C here that's moving with a particular speed, and each person will report a different velocity vector. Okay? So the person in reference frame A will see VC sub A. Okay? That means the velocity of C with respect to A. And then observer B sees a velocity, right? And that would be VCB, the velocity of C with respect to B. And the relationship between these two follows Galilean relativity. We will add in here the velocity of the reference frame, and that creates a transformation, so to speak, between the reference frames so that they can agree upon the speed of things. Now, if you take the derivative of this, okay, the VBA is a constant for sure. And so that means the accelerations must be the same in the inertial reference frames. Okay. So according to the stationary frame, which we're calling frame A, charged particle moves through the magnetic field and should experience a force that's upward. Okay. So Brittany's got to see a force too. Okay. You got to see a force too. And we can see here that the magnetic field, at least in Brittany's frame, should not be producing a force. But what about an electric field? Now, there is an electric field present here, because of the charge, but that is not an external field. So this is strange, right? Something is shenanigans is what we want to call it. Shenanigans properly. So how do we get this? Well, if it's not a magnetic field, there's got to be an electric field. If there's not an electric force, oh my gosh. If there's not a magnetic force, there must be an electric force. The electric force must be upward, which means the electric field must be upward. And the electric field that must be observed here, because again, the forces are the same, is E has got to be V cross B. Now, why V cross B? Well, that comes from the fact that the forces in the two reference frames have got to be the same. So what we have here is we have our electric force equal to the magnetic force. Now, the electric force is going to be QE, simple enough, and the magnetic force is going to be Q V cross B. We'll drop the Q's out of here, and we can see where this relationship comes from. So this is a pretty wild relationship, because what it says is that when reference frame B moves with respect to A, and there is a pre-established magnetic field, that will actually create an electric field in the moving frame that is responsible for this force. Okay, it came from just equating these forces together here, but this is a translation. And the implication of this is again, let's look at this real carefully here. The magnetic field in A, all right, establishes an electric field in B because B is moving. So now, is that shocking? No, because what the heck was all that electromagnetic induction about? It was about moving in a magnetic field. Current. Well, we've already seen that before. We've just packaged it in this way that makes it look sort of different here. And the conclusion we draw from this, because you can switch this around and create a with what if you had I think I'm going to talk about this, so I'm not going to say it yet. So whether a field is considered to be an electric field or a magnetic field really depends upon the frame of reference. What one calls magnetic field, somebody might say, not that the fields replace themselves. I don't want to imply that they replace themselves, but what happens is components of the field can change. So what happens here is we have an electromagnetic field. In reference frame A, that electromagnetic field is a magnetic field, the traditional magnetic field. And in the moving reference frame, the electromagnetic field is partially due to the magnetic field, but there also is an external electric field due to the motion, which is responsible for providing this force here. So it's not as if these things replace each other. It's just that components can transform and they can be seen differently. But the strongest implication of all of this is that there really is no distinction between these two. It's a tenet of physics that the laws of physics are the same in all inertial reference. So whether you see something as electromagnetic is just semantics, really. All right, Sharon runs past Bill, holding a positive charge in Bill's reference frame. There is what? What does Bill see? Bill's showing a little chest here, looking pretty stylish. He needs a hair dye though. I don't like this hair. What color is this? This is a weird color. It's like a who's that guy from who's that dude from America's Top Model? What's his name? Gosh, he had like this slick silver hair. It was beautiful, man. I got amazing skin too. What was his name? I don't know.
Is it Anderson Cooper?
No, oh no, this is not as dark. No, it's America's Next Top Model. The judges. It was. Oh my gosh, it's been so many years. In so many years since I've seen this show. Oh, it's this guy. What's his name? I don't see his name here. J. Manuel. J. Manuel. Sharp guy. Anyway, all right. Bees, huh? I don't think so. I think we're seeing a magnetic field as well, right? Why are we seeing an electric field? Because there's a charge, right? Why are we seeing a magnetic field? Because the charge moves. So we actually see both. We actually see both. Great. Now, follow-up question here. Yeah. What does Sharon see now? What does Sharon see? A's and B's and C's and D's. There is chaos in the chat. And no Bill C test. All right. Oops. Electric field only, right? The magnetic field would be caused by a moving charge. Sharon doesn't say there's a moving charge, so there would only be an electric field here. Okay, good. All right, so this here is our full Lorentz, well, that's not full Lorentz, yeah, it sort of is. This is a combination of the electric and magnetic fields working together to produce a force. So what we see here is the V cross B. That is an induced electric field because something is moving in the magnetic field in reference frame A. So that would be like EB, basically. This would be EB. And you add that to the pre-existing field, and that would represent the full amount of charge that acts on that particular particle there. Okay, so all this together. So I mean, this is basically Lorentz law. This is magnetic force plus electric force. But since from our earlier discussion, we've identified that V cross B really is a magnetic electric field seen in reference frame B. Here is what reference frame B entirely sees. Entirely sees just an electric field because they move along with the charge. And so if we have to equate those two together, this whole thing here has to be equated with this thing here. Now this V cross B is the induced field, but it adds into this. And in fact, it's really this whole statement here. I should just be clear about that. This whole statement is EB. The electric field in reference frame B. The second term here, though, is what we would say is induced, and the EA is what is already existing there. So you can see here mathematically, we're not replacing a field, we're simply adding to the components, or taking away, or whatever. So. All right, I already said this. All right, so let's do a problem. Jump to my example here. Laboratory experimenter has created the parallel electric and magnetic fields as seen here. They run along the x-axis. We have an EA and a BA. And this green vector here is a velocity, okay, of B relative to A. Now B here, proton is shot into these fields with a velocity of 1 times 10 to the 5th. What is the electric field in the proton's reference frame? So, in the ground frame, there's a magnetic field and there's an electric field, right? Because of the motion of the proton here, proton's not the object we're interested in here necessarily. We're interested in what the fields look like in the reference frame. So we have a ground frame, which is what we're calling A, and we have a moving frame, which is what we're calling B. So the velocity here represents the velocity of the reference frame. We want V cross B. So if you did V cross B, you take your fingers and you line it along Y. We're going to open our palm towards X, and our thumb points down in the negative Z direction. So the electric field's already going to be here. You're not going to really get rid of that. But what happens is you now have an induced electric field that also points downward, and you'll need to combine these two together to figure out the overall electric field seen by the proton. So it's the same statement we developed before here. V cross B creates an induced field, which adds to a pre-existing A field to get our field in the reference frame of B. So I put in here 10 to the 4 I hat. That's what the strength of the electric field is. And we're going to add to that the velocity, which is 1/10 of the 5th times a 10th of a Tesla here. Now, J cross I, if you remember the little trick I showed at the triangle thing, is minus K, or you can just do the right-handed rule to get that. So we see here that this field completely changes direction, actually. In one reference frame, it goes completely along the x-axis, and then now in this reference frame, that moves quite fast, actually. The electric field makes this angle with respect to the x-axis and the negative z-axis here. And that's what our new electric field is. So you see, while you can do this, what does it require? Well, I mean, the magnetic field here is not too big. 0.1 is kind of moderate. That's fast speed, though. But then again, this electric field is pretty darn big, too. If you lowered that field, you could lower the speed here. So these are moderate, relative to each other. But magnetic fields tend to be just lower in magnitude, generally speaking. Okay. Let's keep going with this. Where's my slides? Here they are. So now the top equation is what we just earlier developed. And not going to go through the full derivation of this, but you can do the exact same treatment for magnetic fields. A V cross E is going to be an induced magnetic field here. It's given by minus 1 over c squared is the coefficient that's here. Again, what you do is really go through the same arguments where you sort of say, okay, we're trying to figure out what the magnetic field's here. If we move in an electric field, it's going to induce a magnetic field. So if you say, for example, you don't have a magnetic field in the stationary frame, but you do have an electric field, if you move relative to that that field, it does create this induced field here. And when that's combined with BA, gives you the overall field that's seen in B. So it's the same argument. The c squared might be sort of surprising here. And again, it's just sort of the details of how this is derived. Again, I don't want to go into it because it's take a lot of time with not a lot of effort, not effort, but benefit. Of course, your book derives the Galilean transformation equations, but this allows you to go back and forth between the systems here. Now, while these equations here are specifically for what the electric and magnetic fields are going to be in reference frame B, you can very easily get what it's going to be for A. Okay, the trick here is this. Swap subscripts on everything. All the B's become A's, and all the A's become B's. But if you do that, then you got to realize that swapping subscripts takes one of the reference frames that makes it moves in the opposite direction. So what I mean is this. If A is stationary and B is moving to the right, okay, well then make B stationary. That means A moves to the left. Okay, basically the statement is this. The velocity BA is minus the velocity AB. So if you go here and you make this plus sign a negative, and you make this minus sign a positive, and you swap all the subscripts, now you have statements of what the electric and magnetic fields in A would be if you knew what B was. Okay, so I don't know if you knew that trick or remember that trick from reference frame stuff, but swapping subscripts just require you to switch velocity signs. And of course, all this stuff here does require that the speed be significantly lower than c. How much lower? You want to stay under 10% speed of light, and these corrections are, the corrections are small. Over this 10% speed of light, things become significant, and you really got to change things up quite a bit. Not quite a bit, really. So, okay, so here's the thing with the C in here. It comes from QuickCheck, coulombs and Biot-Savart law. There's a lot more algebra that's involved here, but C ends up being, oh my gosh, 1 over radical mu naught epsilon naught. And that comes again from combining the equations here. And so what happens is what this equation ends up being here is this. BA minus VB. Oh, I don't know why my thing does this. And then it's all divided by mu naught epsilon naught. And each one comes from either Biot-Savart or Coulomb. But when you actually work out the mathematics there, the square root of that ends up being the speed of light. It also comes from the wave equations, but we haven't covered wave equations. If you take physics 211, we do cover wave equations. Once you have these transformations, you can develop the wave equations and you can solve for what the speed of the wave is. Because as it stands, you would just leave this as mu naught epsilon naught. But when you start to apply this to the wave equations and you work out what the speed of the wave is, you find the speed of the wave is this quantity here, 1 over radical mu naught E naught. So, and it's strange, but yeah, the units of this thing ends up being meters per second. So that was a very important discovery. It was something that was formalized properly by Maxwell, was the realization that light and electromagnetic waves are the same phenomenon. I mean, we take that for granted now. Well, I don't know. I teach a lot of astronomy, and some people take it for granted. Some people have no idea, regardless. But yeah, light is just a representation of electromagnetic waves. That's it. It's the visual sign of those things. Right. Let's do another problem here. So we have our transformation equations now. All right, scientists in the laboratory create a uniform electric field, 1 times 10 to the 6 in a region of space where there is no magnetic field. We would like to know what the fields are in the frame of a rocket traveling in the positive x direction at 1 times 10 to the 6. So we want the EB equation and the BB equation. BA is 0. So that makes the first equation rather simple. The electric fields are identical. If there's no external magnetic field, there's nothing to induce an electric field. So the electric fields are the same in both. In the magnetic field, though, having a pre-existing electric field will create an induced field, magnetic field. Now, BA is already 0. So we need to evaluate the V cross E to see what this existing electric field turns into when you're in a moving frame. So we got 1 over c squared here. The velocity is 10 to the 6. The electric field is 10 to the 6. I cross k is minus j. Okay, so that would be x-axis, open your palm upward to the z-axis, and your thumb points in negative y. So negative j here. But again, I like my little... It's easier to do the little trick here. The little trick being I, J, K. These form the essence of. All right. And so if you go clockwise here, positive. If you go counterclockwise, negative. So I cross K, negative J. The negatives cancel out, and we get 10 to the 12 divided by c squared, which is already like what? Like 10 to the 16 or something. So the field is 1.1 times 10 to the minus 5. That's like a little tickle of a field. That's like what the magnetic field of the Earth is. Like where you're in your room right now. Okay. Or your car, or wherever you are right now. Under the covers or outside doing yard work or sitting in front of a desk for hours every day with an end in sight, but then it starts again in January. And okay. All right. So anyway, magnetic fields very weak in this context. So that's a large electric field, and that's a large speed. So it doesn't create a huge magnetic field, which is part of the reason why this kind of phenomenon wasn't really noticed for a very long time, because it's just very difficult to measure these kind of things. All right, question for you, just to make sure you get these directions right. Experimenters on Earth have created the magnetic field shown. That's an external magnetic field into the page here. Rocket moves to the left. What's the rocket going to see? What is the rocket going to see? I dare you to answer this question correctly. You bold warriors out there, what are you thinking? D? I don't think I like D. No, I don't like D. I don't like, well, you know what? Let me think here. D is not... The answer is B. Here's the thing. The magnetic field, again, we're not replacing fields. We're adding components and things like that to it, or adding parts to the components. So it is B. I mean, if you say D, you're saying that you're traveling fast enough that you can completely cancel out the magnetic field. No, you can't. No, actually, that wouldn't happen here. No. This field, like if you look at the transformation equations here, look, this field, any field in reference frame B would be whatever it is in A minus this stuff here. Well, if there's no pre-existing electric field, which there's not, there's no way you can cancel this out. So it's still going to be there. B is still there. But because you move in B, you're creating some electric field. So, yeah, it's definitely B. D is not right. You're not going to... Now, D could be right if there is a pre-existing electric field and you really just haul it in this rocket to some speed that just turns out you actually cancel out completely, which is weird, but I suppose... I don't know. I don't know what kind of speeds are required for that. I got to think that that's probably not attainable classically, but I'd have to do the math. All right. So let's go back and revisit some of these laws we developed here. Just to remind you of some of these things, because we want to pull it all together into one thing here. The laboratory reference frame here, when we put this moving loop here into, we're inserting into the magnetic field, this is creating for us a force that is upward, which we've attributed to the magnetic force. That, however, as we know, is going to create a current in the loop. So the motion of this is creating for us an electric field as well. And so that electric field points upward here in order for these charges to move. So if you're in the reference frame, right, if you're in the reference frame of this conducting loop here, you're saying, I see the magnetic field, but I also see an electric field, and that pushes those charges up. So that's how that part gets resolved. This is just the induced field, electric field, Faraday's law. So you remember Gauss's law. This is one of what we called our field equations. It's a surface integral with the electric field. It's equal to Q enclosed over epsilon naught. Do we have a surface integral for magnetic fields? Sort of, yes. I very briefly talked about it. But there really is no Gauss's law for magnetic fields, because here's the thing. Any closed surface you have includes both a south and a north pole. It's like always having dipoles. And always having dipoles means that the flux is ultimately always zero. It's never non-zero. Because if it was non-zero, then you're claiming you can isolate a pole, which you can't do. So this is Q enclosed. You can isolate single positive charges and negative charges. You cannot do that for north and south poles. And if anything, while the north and south might have been helpful to sort of think about interactions and how that might be similar to electric stuff, when we look at this, we see that it's actually very different. North and south just really are about directions of moving charges. So having a north and south is not saying we have different charge states. It's saying it's describing a direction of charge flows. But there's always a left and a right to that. You know, there's always a going forward and something that's behind. So anyway, this integral is always zero. And there's nothing you can really do with this. There's no problems to solve. It's just a fact. So we don't really do much with it. Just kind of say, yeah, that's the thing. We saw this. This is Faraday's law here. This is what we developed ultimately here. That the line integral of E along a path is the change in the magnetic flux. This was all the induced field stuff. Faraday's law, basically. And then we had Ampere's law, which is the line integral for magnetic fields, and that was equal to the current that's enclosed here. Now, there is a small correction we have to make to this. And it's something that we didn't talk about in this class. It's not part of the curriculum. But there is one extra piece to Ampere's law that was not discussed. And you can see that in this example here. If we have a capacitor, right, that's being charged here, and we put a path around this thing, you know, there's a current coming into the left here, but there's no current over here, but somehow there's information transmitted that allows the current to come through here. So while it looks like a broken loop, there must be something here in the field equation that takes the place of a current. It's the only way this really makes sense here. So it is incomplete Ampere's law. It looks at the motion of currents and how magnetic fields are going to look with those, but in empty space you can have something that's called the displacement current, and that's what's seen here. So this displacement current is a change in the electric flux with time, and that is a type of current. It does have units of amps actually. And if we look at how the electric flux through the surface increases or decreases, that is what we call a displacement current, and it takes the place of this charge current here, and it allows Ampere's law to still be correct, basically. So that's the statement on the right here is equating these two sides. We have a current on the left here, and on the right, we're looking at how this charge is increasing in time, which is just a statement of current, actually. So the full Ampere's law actually looks like this. When we create our path, we are concerned with what charges, what currents go through there, but we're also concerned with any changes in the electric flux. These problems are a bit harder to solve, and they don't have a lot of practical applications. That's why they're not really part of the curriculum. That's why we didn't talk much about that. So here it is. Here it is. This is all of electricity and magnetism in 4 equations. These are called Maxwell's equations. James Clerk Maxwell just summed up 200 or something years of work in classical electromagnetism and created these monsters. Of course, you see there's different names attached to them because these ideas are developed over time. But it was James Clerk Maxwell that first sort of sat down and formalized this all into one grand theory. And so from a classical standpoint, not considering any quantum or special relativity, these equations explain all electromagnetic phenomenon. All of it. These equations here. Now, there's some good things about this and there's some bad things about this. Here are the good things about it. It's beautiful. It's elegant. It's 4 integrals to our surface, closed surfaces, to our closed paths. There's relationships between electromagnetic fluxes. Everything about this is amazing. Now, differential form requires some vector calculus. You throw in a bunch of curls and divs, and that's equivalently what these are. It's fundamental law calculus kind of thing stuff. So, all right, so the full Lorentz force law involves electric and magnetic fields. So that's the only other thing you'd really have to specify, although you can specify that. You can get that out of here eventually, but this equation is sort of links up with other aspects of physics. But this is, you've reached the end you've basically reached the end of classical physics. You learn all of Newton's laws, kinematics, gravity, all electromagnetism. You haven't taken thermo because that's in 211, and there's a tad bit of optics that's part of that. But optics ultimately can all be derived from electricity and magnetism. You could argue that thermodynamics is derived ultimately from mechanics, I suppose. No, there's laws in thermodynamics that seem separate. But anyway, this takes us to the end. The end. You are living in the year 1899. Is that what year we're in right now? We're living in the year 1897. What did I say? 1899? 1897. 1897 is what year we live in right now. And is there a date on this? Come on, Wikipedia. Don't you do this. What year? No year. Oh, it was before April 30th. So before April 30th in 1897, we didn't know what electrons were. And J.J. Thomson, not to be confused with the director, but he discovered the electron, which is what ushered in the start of modern physics. I mean, there were observations made prior. The Young double slit experiment was like part of that. What the heck is going on here? But there's no theory about it. Let's see what else. I mean, there was a lot of things with regards to atomic spectra that were known but not understood. I mean, when was helium discovered? Was that a long time ago? '1895. 1895. Crazy, only 2 years prior. What an exciting time to be alive. Probably not, because I would have got dysentery, but whatever.